Today we're talking about significant digits, or what some people call significant figures. We usually short form them to Sig Digs or Sig Figs. Probably me personally, I'm going to call them Sig Figs most of the time. It doesn't really matter so much what we call them is A, how do we get them, B, what do we do with them. We better start out with talking about what they are, first of all. And it comes down to the fact that there's two kinds of numbers. Now, I should have said before I started this that in terms of writing notes down, I mean, oftentimes with the videos you are required to write, well, not required, you're expected to take a certain amount of notes. Here it's a matter of being able to use Sig Digs or Sig Figs. But let me know, getting back to it. So there's two kinds of numbers. There are things that are known to be exact values. And when we're talking in chemistry, exact values are going to be counted values. So if we're talking about a chemical formula, for example, we understand and we take that there are 2 atoms of hydrogen for every 1 atom of oxygen in a molecule of water. So we don't have to worry about inexactness in that. There's also certain defined values. So 1 liter is defined to be exactly 1,000 milliliters. So we don't have to worry about any kind of inexactness there. However, we also have measurements, and measurements have a level of inexactness to them. And or uncertainty is probably a better word for that. And what that means is, if I take a measurement, it's not going to be precisely a certain amount. I might report it as a certain amount, but there's always a little bit of uncertainty there. And the amount of uncertainty depends on the spaces in the measuring tool. So for example, if I'm measuring centimeters and I have a ruler like this, the graduations, the biggest lines, are between full centimeters. Whereas if I had a different kind of ruler, I still might be measuring centimeters, but now the centimeters are divided up into millimeters. So the one ruler is going to be much more precise, going to give me a better answer than the other. Okay, so when we talk about measurements and in uncertainty, we need to define a couple of terms. And again, not something we have to write down, it's just you can hear these terms. One is accuracy. And if I have a number that is sort of, this is the correct answer, accuracy is how close am I getting to that right answer. So we'll have theoretical values, and those we will take as our true values. But if we're trying to figure out what those are from an experiment, well, the experiment is never going to give us the correct or the true value, because the true value is theoretical. Then there's precision, and that effectively comes down to how good was my measuring tool, which turns into how good is my measurement. If you have a thermometer that says, and you say, oh, it's 15 degrees, is it exactly 15, or is it 15.3, perhaps 15.1, perhaps 15.4? Any one of those would round down to 15, and 14.7 would round up to 15. So I can have a fairly decent sized temperature range. I'm still calling it 15. Okay, if you were to take a look at a comparison between precision and accuracy on target shoot, well, that's neither accurate nor is it precise, because the bullseye would be the true value, or the target, and then precision is basically how close am I to each value. So then we have some results that are fairly precise or close to each other, but they're not very accurate. And finally, we have some values that are getting close to accurate, but they're not very precise because they're still scattered around. And then the best case scenario, well, and you could probably even do better than this, is examples where they are fairly precise, close to each other, and they're also fairly accurate, close to the true value. Okay, if I'd given you a thing to measure, and I'd given you that ruler that we saw in the first one, if you were to look at that, you'd probably say it's a little bit more than 2, certainly not quite 3, maybe it's pretty close to 2.5, but not quite 2.5. You could estimate the first decimal point. And when I did that, I would have called it about 2.3 centimeters. On the other hand, if I took a more precise measuring tool and I look at it now, if you look carefully, it's not quite 2.3, but it's not quite 2. It's a little bit more than 2.3, but not quite 2.4. Maybe it's a little bit closer to the 2.4. I would estimate it to be 2.36. The point is, I can always estimate in between my actual graduations. And that's kind of important. It also, however, brings us back to significant digits. When we talk about digits, which ones are significant? And we have a chart that is going to end up setting the rules for deciding how many significant digits there are going to be. And then we're going to have, well, what if I'm doing mathematical calculations with numbers, because we do that. What does that do to the significant, or how many Sig Figs there are? So leading zeros are not significant. Trailing zeros, this is where you're going to find differences of opinion, because for me personally, that's 64,000, or 6,400, I should say, 6,400. I would call that 2 significant digits, but I do know of people who would call that 4. I would know of people that say if you want to call it 4, then it should be 6400 decimal. Okay, I'm going to go with 2, but again, that's one where you're going to see some variation. 10.0, I don't think you'd see any variation on that one. That final 0 is going to be considered significant. If you're talking about scientific notation, all of the digits that are included are significant, and if you're talking about some counted values, well then those are now exact values. Remember we had that from earlier. Then you're not talking about any level of significance because they're not measured. Okay, that's really what it comes down to. If you're measuring, you have to talk Sig Figs. So masses, lengths, volumes, any kind of measurement. Now for us, it's going to become an issue both when we're measuring in labs, but also when we're doing calculations and other questions. So we need to know what to do here. If you're adding or subtracting, then you're going to be doing a rounding off to the least number of significant digits. The best way to think about this is if you line things up in their columns, like your ones and tenths and tens and hundredths columns, the smallest number of decimal places would be your what you would round things to. So if you took a look at this, my first value there, 1.7, if it were 1.70, it'd be a different story. But because it's 1.7, I can't count on the significance. I can't count on significant digits past that 1.7. So I round everything to 1 decimal point. The difference now, though, with multiplying and dividing is that with adding and subtracting, I'm looking at decimal points. With multiplying and dividing, now I'm just counting Sig Figs. So on my add subtract, I went from 2 Sig Figs in my very first value to 3 in my final answer, but 1 decimal point in both. With multiplying and dividing, it's rounding off to the fewest number of significant digits. So if I take a look at here, one of my values has 2 Sig Figs, so my final value has 2 Sig Figs. And it doesn't really matter if there's no decimal points at all, 2 Sig Figs. One of the things that we're going to be doing as we go through the calculations is we're going to be aiming to be using Sig Figs all the time. Same thing with labs. We're going to be aiming to use Sig Figs all the time. But it's going to be part of a growing process. So it is also going to be a growing process in terms of when do I start really counting on you using Sig Figs well and perfectly. So we'll try to make sure we get a lot of practice at that. But the bottom line is Sig Figs is important in any kind of science where you're making measurements. So we do have to make sure that we carry it along. It's going to take some time to get used to it, but we'll get used to it. We'll talk to you in class.